titled Tasks for U4L18. The do now is task number 1. It's just a Google form. It is not graded. It is about 4 or 5 questions, 2 multiple choice and 3 free response. And it's all based on this orbit simulator, which is pretty simple. There's a little control panel here on the right. I have instructions on how to use it, so just follow the instructions and answer the questions, and feel free to play around with it as well. I'm going to time this for 8 minutes, and then we'll come back together to review. So let me know if something doesn't work, if you need help, but otherwise go for it. 8 minutes to do the do now. All right, kiddos, 8 minutes has elapsed. Let's come back together. Looks like we've got about 8 responses, 11 of us in the class, so looking okay. All right, glancing over responses, we're looking pretty good here. So obviously when you have the simulator run for everybody, okay? So you start off with a planet and a moon circling it, could be Earth and the moon, but when you just run it, you get something like that. What kind of orbit is that?
Circular.
Circular, right? Because elliptical, again, remember elliptical would look more like that. Decaying would look something like this, and escape would look more like, whoop, like that, right? So that's circular. Looks like we're feeling confident there. So when you increase the mass of the planet, the moon gets pulled in a little closer. Why does that make sense? What do we know about the relationship between mass and gravitational force?
It's directly proportional.
Bingo, right? If you were to increase the mass, then you're going to increase the value of the gravitational force, right? They're directly proportional. And that's literally just a demonstration of that. And I guess just the increased gravitational force pulls the planet into a closer fall around the planet, or a closer orbit. So when we drastically increase the mass of the planet, then it looks more like this. What do we call that?
Elliptical orbit.
And what did you notice about the speed of the elliptical orbit when it was closer versus farther away? Or did it move faster? Closer or further away?
Closer.
Much closer. Do you guys notice how it kind of slingshots around and slows down and slingshots around? So it kind of reinforces what we were learning before about elliptical orbits and their properties. Kind of cool. And then obviously, if you were to drastically reduce the volume of the moon, what happens to it? What is it achieved?
Escape velocity.
Yep. And so there's nothing holding it to the planet anymore. It can shoot off in its own direction. Presumably, though, if this was the Earth and the moon escaped the Earth, does anyone know what the moon would eventually fall into orbit with, though? Like, what's the really, really big thing in our solar system that everything is gravitationally attracted to?
The sun.
Yeah, right. It would still probably fall into orbit around the sun, might even fall into the sun. But that's something you'll actually play around with. So one of our main activities today in class is going to be to work with a fancier orbit simulator that's actually made by the PhET organization. This was just kind of more of a warm-up to make sure we're feeling good, which looks like we are. Any other questions or feedback on that? All right, and that simulator is actually fancier than you think. I didn't do anything with this, but that little arrow, the arrow that's on the moon, you can change that to change the initial velocity, and you can actually click and drag the moon anywhere you want for it to start. So you can actually play around a little more complicated way with that. So before we get on to our main content, I wanted to have a chance to review the homework. So were there any questions or anything you wanted to help on, or anything you left blank from chapter 28, questions 1, 3, 5, 7, and 9 from the reading check at the back of the chapter?
Can we go over 5?
Yeah, I was going to say 5.
5? Okay. Yeah, 5 is definitely a little unclear because it says, according to the nebular theory, did the planets start forming before or after the sun ignited? Now, the chapter starts off immediately by saying that everything formed when? Their opening statement is that everything formed at the same time, which is really unclear because, I mean, yes, that's true, but the sun hadn't ignited, right? That the sun was basically the largest ball of mass that was in the middle of our solar system, and then there were lots of little tiny ones forming around it, encircling it. That's what eventually became the planets. But yes, it all started at the same time, but then only once the sun had such a large amount of mass that it began to experience fusion reactions inside its core. The gravity got so strong that fusion reactions started. That's when it ignited. And so the technical correct answer would be that it started before. So planets formed before the sun ignited. When the sun ignited, it definitely changed the way planets were forming. Did anyone catch on to this? So what state of matter, solid, liquid, or gas, are all the inner planets, the 4 planets that are closest to the sun? They're all what?
Solid.
They're all solid because, again, they had started to form. Then the sun ignited and basically cooked them, right? Like it basically baked them into these hard stones. Whereas the outer planets didn't quite solidify in the same way. They're gaseous giants. They're way bigger. They don't have the density that the inner planets do because of that influence of heat and gravity from the sun. So anyway, kind of interesting. So I hope that clarifies it. The correct answer is before. They started to form before the sun ignited. The sun ignited, during this whole formation process. So pretty crazy to think about. Good question. Any other ones? Feeling good about the sunspots one and everything? That was something I didn't realize. I thought that was really cool about the sun. I didn't realize. So anyone know what state of matter the sun is? Solid, liquid, or gas?
Liquid.
It's actually mostly liquid, which is weird to think about. Yeah. And so liquids don't orbit, don't rotate at the same velocity, right? The equator of the sun moves a lot faster than its northern and southern hemispheres. So you get these eddies, almost like the hurricanes we learned about when we were talking about earth and wind. And that's what creates those little sunspots, those little magnetic dead spots. So anyway, kind of cool stuff. All right. No further questions on that, then we can move on. So the next activity is you're going to be using a PhET simulation, very similar to what we were just doing for the do now. I'm going to ask some more detailed questions. PhET simulator looks like this: gravity and orbits. There are 2 things. There's 2 scale and model. I encourage you to play around with the 2 scale one because it kind of puts things in perspective, but we're going to work with the model to start. You're actually going to be using 2 different options for this. It'll start here with just the sun and the earth, but I first want you to click the 3rd one down right there in the control panel in the upper right, where it's just the moon and the earth. You'll answer some questions on that after following some instructions, and then you'll use the next one up, which shows you the sun, earth, and moon, and you see some really interesting dynamics there. There's a little Canvas quiz. I've linked to it that looks like this. It's 4 multiple choice questions based on observations from the PhET. And then a 5th activity, which is actually a Flipgrid post. You're going to need to capture your screen. So film your screen. There's a certain task I want you to try to complete using the PhET simulation, and then just post a short video of that. It's pretty straightforward. If you just, right next to the record button, there's 3 dots for like more options. Click on that, and one of the options is screen capture. It's a beta program that it runs. It might not work on everyone's computer. If it doesn't, just use QuickTime, or if you have a Mac with Mojave, you can use Control-Shift-5. Pulls up an automatic screen recording on Macs running Mojave or later. Anyway, let me know if you need help if something isn't working. We'll find a way for you to upload your recording. So all the instructions are there on Canvas. I even have videos on how to use the PhET simulator, a video on how to record your screen using Flipgrid. So if you're not sure what to do, you can watch those. But otherwise, I'll be here. Let me know if you need help with any of this. I'm going to time us for 20 minutes. And again, just check in with me if something isn't working, if you're not sure what to do. Okay, go for it. All right, kiddos, 20 minutes has elapsed. Let's come back together. Looks like about 10 of you were able to submit your quiz and post your videos, which is great. If you're still working on it, that's okay. This will just roll over into homework where you can continue working on it once I let you go on the next task. What did you think of this simulator? A little fancier? It's kind of fun to play with. Again, I suggest go to the other option, the 2 scale one, which first of all shows you how tiny these planets actually are compared to how far away they are. But then it's fun to kind of mess around with the gravity and see what you can make Earth to do. Most people are able to get the moon to fall away from Earth, but to not hit Earth. Again, it's kind of fun to play with. It all kind of almost depends on when you change the settings. Like some of you I saw, you reset it, you made the settings and you just played it. Others were letting it rotate and then you would change it suddenly and it would fly off. But yeah, Olivia?
Are the multiple choice questions graded? Because the trail of like the moon, the path doesn't make a full rotation. It kind of like disappears. And so like for the first question where I was asking how many Earth days, I didn't like remember like where the moon like properly started, and so I kind of like might have overshot it, and it says I got it
Yeah,
wrong.
I noticed you weren't the only person. Quite a few people select 31 days, even though if you play the simulation through, it's technically 27 days. That's what I was getting with that. But yes, I can give a point back for that if you were not feeling good about, yeah, because again, it was a bit of a weird question as well. So, but yes, that was the first question. So if you let the moon do a full rotation, according to this simulation, how long did it take?
27 days.
Yeah. Which again, you're right though, that we think of this cycle of the moon as more being close to like 30, 31, 29 days. Does anyone know what we call that in our calendar? There are 12 of them in a year. How do we refer to a full cycle of the moon?
Months.
It's a month, right? That's what months are based on. But it's got fascinating stuff with biology, right, as well, that a lot of life on our planet has evolved with these cycles, right? Hormone cycles occur over a month, like menstrual cycles often occur over roughly 27, 28-day cycle. There's a lot of other examples you can look at in things from bacteria all the way to plants that they follow this cycle of the moon, which is kind of cool. It also has a pretty big like religious significance in a lot of things. Islam in particular, Muslims are very moon centered, right? That religion, the symbols, the moon. There's certain months out of the year. In fact, we're in a very special month right now for Muslims. Anyone know what people practicing Islam are doing right now?
They're like fasting for Ramadan.
It is. It is Ramadan. So they are fasting. So for a whole full cycle of the moon, for a month, they do not eat or drink anything while the sun is up. And so it's one of the 5 pillars of Islam, and it's meant to sort of, it's their way of sympathizing with the poor and with people who don't have food. And it's pretty incredible show of faith, in my opinion. But I lived with a Muslim family for years when I was in the Peace Corps, and it was really fascinating to see when it ends, right? They're all very excited for Ramadan to end because it's been tough to get through. And there's usually like a radio broadcast or TV broadcast that kind of officially says like, okay, we've announced the end of Ramadan. You can now, eat. And but some people are kind of sticklers, and they're like, no, even when the announcement goes out, they won't end their fast until they've actually seen the new moon, right? So they literally go outside. My host family was like this, and they're all staring at the sky, looking for like a little sliver of moon. But then they're like, okay, the moon has made its full cycle, and they can eat again. So anyway, it has a religious significance on our planet as well, which is kind of cool. I also really like the detail in this simulation. So what did you notice about Earth? Does Earth stay perfectly still as the moon rotates around it? It's kind of cool that it's almost like 2 people swinging on a rope or whatever, that one is also, the moon or Earth is also moving just very slightly. And the moon's pull actually has a significant impact on our planet, and we can see that with our oceans too, right? Tides and waves are all made possible by the action of both wind but also the moon. Similar example, when we increase the gravity, the moon gets pulled in a little closer, falls into a what was the question we asked here about that? It falls into elliptical orbit, right? It falls away from Earth instead of moving. And yeah, this is the one where you turn the gravity off and then it just floats away. Yeah, and that obviously then, unlike in our do now one, even Earth would then probably shoot off and not rotate around the sun or anything like that. I think the coolest thing to take away from this is then when you're looking at the sun, moon, and the Earth all together, and if you turn on that path, did everyone notice it kind of almost looks like a little flower pattern, and it just kind of hops around? And so, yeah, it's sort of an interesting detail. And if you look at the velocity arrow on that one, it technically isn't just doing a consistent velocity around Earth, but in reality is more getting sort of tugged forwards behind the Earth and then slows down a little bit as it cuts in front and behind. And so it's sort of interesting that apparently the moon doesn't actually have a consistent tangential velocity. It depends on where Earth is in its rotation, right? Things get complicated when you start taking the sun into account as well, and how the Earth is moving around the sun while the moon is moving around Earth. And then you could play around using the flip grid on how to mess that up so that the moon actually falls away from our planet. Were most people able to successfully record their screen? Okay, again, let me know. You can send me an email of the video too or something like that if you can't get Flipgrid to work. So, all right, any other questions or comments on that activity? So what I wanted to conclude class with was a drawing activity where I'm actually going to have you now on paper draw a circular orbit and an elliptical orbit as best you can. And the way we're going to do this, since I know not everyone has a compass or things like that, where you're going to use pins and string. I have instructions on how to do this. So if you take a look real quick on Canvas, this is now task number 5 here. And I have a whole instruction video. I have written instructions on what to do, but there are some things that I want you to calculate about these orbits as well. And so I've got to teach you a little bit of geometry, a little bit about shape stuff. So before we talk about planets and moons and orbits and stuff like that, let's get down to the basics. That an ellipse is anything that's based on 2 points called foci. 2 focus points is basically what they call it, right? And you've drawn around that. Now you'll do this by putting pins in these 2 locations and using string to sort of guide your pencil all the way around. It's pretty straightforward. But what I want you to do for the ellipse that you draw is to calculate what's called the eccentricity. Is anyone familiar with what eccentricity is? Anyone know what we're describing about our ellipse?
How circular it is.
Bingo, how close to a circle it is. Circles have an eccentricity of 0, right? So they are circular. So the closer to 0 your eccentricity is for your ellipse, the more circular it is. The further away from 0 it is, the more elliptical your ellipse is, okay? And this is calculated in a simple equation. E equals C over A. If I'm correctly, I keep doubting myself with numbers. Yes, C over A, like that. So all you need to do is figure out what these 2 values are, C and A, and it's pretty straightforward, but there's just one more added step you have to understand. In order to find and measure your C value and A value, you have to find the center of your ellipse. Anyone want to guess how we can find the center of the ellipse? What could we measure?
The distance between the 2 points.
Yep, and then divide by what? Yep, divide by 2, divide it in half, and that is technically your middle, okay? So your C value and A value, now, as I said, you're gonna be either close to or far from 0, so the C value is gonna be a small number, the A value is gonna be a big number. And the reason why is because C is the distance from the center to one of the focus points. That's your C value right there, okay? The A value is your distance from the center to the outermost point, the outermost axis of the ellipse. So in other words, you're going to have a big measurement divided by, or sorry, you're going to have a small measurement divided by a big measurement. That's the trick, okay? You're going to have a whole video explaining this. I have written instructions too. This is the only hard part where you've got to kind of set up a little bit of math. There's no unit on this number, so it doesn't matter what you measure it in. If you measure in centimeters, measure in inches, as long as you're doing the same thing, the units will cancel out. You can use a ruler or the Measure app on your phone too. If you don't have a ruler at home, works really well as well. So that's eccentricity. You're then also going to draw a circle. And I think a lot of you are hopefully familiar with geometry at this point. But for the circle, I'm going to have you calculate the circumference. Does anyone know what the circumference of a circle is?
2 pi r.
Very good. The equation is 2 pi r. But what am I describing when I say circumference? What is 2 pi r actually telling you?
The distance around the outside of the circle.
Yep, so if I took that line, straightened it out, how long would it be? So you are going to have a unit here. If you measure in inches, your circumference will be in inches. If you measure in centimeters, your circumference will be in centimeters. Does anyone know the value of pi? Give me the first 3 digits.
3.14.
3.14, right? 722 divided by 7, or however else you want to calculate it. So, all right, I have written instructions on all of that. Your ultimate goal is to draw something like this, where you've got a star in the middle. You have one planet in an elliptical orbit and one planet in a circular orbit, which is a little larger. And I'll walk you through in the video and in the written instructions on how to do that. So this will probably end up rolling into homework more, but we'll at least use some time to get started on it. I want to be back here by 9:35, so that gives us 10 minutes to work on this right now. So I'll time you for 10 minutes, read through the instructions on Canvas, watch the video if you want. But you've got 10 minutes to work on task number 5 before we come back together to conclude. So again, I'll be here listening if you've got questions or need help on anything. Go for it.